Every wave has an energy associated with it. The energy we receive from sunlight and the destructive effects of an ocean surf and earthquakes bear this out. As an example, let's consider again a transverse waves on a string. How is energy transferred from one portion of the string to another portion of a string? So let's focus on an infinitesimal small element of the string. So I'm gonna identify that in here, and let's call this one to be a mass of dm and has a length of dx. So we have a blade that oscillates in simple harmonic motion, and the string is attached to this blade. So therefore, each particle or each element of the string also oscillates vertically as the blade does in simple harmonic motion. So in other words, the motion of this tiny element that we have is vertically going up and down as the blade does. Now, if the blade is going up and down, it moves, so there is a transverse velocity, so therefore there is a kinetic energy associated with the moving element. So if we write the kinetic energy of that moving element, that would be dk equals 1/2 the mass of that tiny element times v transverse speed squared. Now let's suppose originally that the string has a mass density, linear mass density m. Then our dm, tiny mass of the mass of this tiny element, will be mu times dx. Okay, so let's plug that in into our expression for the kinetic energy. That'll be 1/2 mu dx vy squared. So now let's recall what we found for the vy as a transverse speed. We derived it in earlier version of my videos, pencasts, that equals omega a sine kx minus omega t. So I'm going to plug that in here. Then the dk would equal 1/2 mu omega a sine kx minus omega t squared dx. So if we take a snapshot of that wave at the time equals 0, that time equals 0, like when time equals 0, then our dk would be equal 1/2 mu omega a sine squared kx dx. Now, if we integrate this expression over all the string elements in a wavelength, then in a wavelength which is the lambda, which means our integration is going to go from 0 to lambda. So then the kinetic energy over the wavelength, that's a lambda, that's why I'm writing a lambda here, equals integral of dk, which equals integral that goes from 0 to lambda 1/2 mu omega squared a squared sine squared kx dx. Well, let's rewrite this in a nicer way. 1/2 mu omega squared a squared are constant. They come out from the integral 0 to lambda. So I have a sine square kx dx. Now we have to evaluate this integration. For that, let's do a quick recall. And of our integration of our integration skills. You can also find this in the back of your book. It's a chart. It's a tabled integral. So integral of sine squared ax dx equals x over 2 minus sine 2ax over 4a. Well, if you want, you can evaluate this, try your best. But we're not focusing on that now. So I'm going to use this integration, this integral to solve, to evaluate my expression. So that equals, so that equals 1/2 mu omega squared a squared. Okay, so I'm going to write it this way. X over 2 minus sine 2kx over 4k, and then I have 0 and lambda for the limits. Okay, so let's go ahead and do this, continue evaluating this integral. Actually, I need to continue on the same side. So let's do this. So that equals 1/2 mu omega squared a squared. Okay, so I'm going to plug in the values, okay? Lambda over 2 minus sine 2k lambda over 4k minus, so we have a 0 minus sine 0 over 4k. Okay, so this would equal 1/2 mu omega squared a squared. Well, this term in general is a 0, okay, so we don't care about that. But here's one thing that we want to take care. Let's look what is the k. So we know that the k equals 2 pi over lambda. I'm going to substitute that in there, okay? Then I would have times lambda over 2 minus sine 2 pi over 4k. Well, sine of 2 pi is, we know it's a 0, so this term is a 0. We end up having this simple form of 1/2 mu omega squared a squared lambda over 2. So we can also write that k lambda equals 1 over 4 mu omega squared a squared lambda. Okay, well, with the similar analysis, we will find the potential energy over the wavelength also equals 1 over 4 mu omega squared a squared lambda. So you can try it on your own. Now, to find the total energy, that will be kinetic, total mechanical energy, that would be kinetic energy plus potential energy, which if you add these two together, you will get 1/2 mu omega squared a squared and lambda. As the wave moves along the string, this amount of energy passes by a given point on the string during a time interval of one period of oscillation. Therefore, the power that is associated with the mechanical wave, the average power, so we can write either average or we can put the bar on the top, it doesn't matter, equals total energy mechanical over the period of the time, because it's one wavelength distance is energy per wavelength that passes through the wavelength. It actually takes one period time. So that equals 1/2 mu omega squared a squared lambda over the period. Well, let's recall what is lambda divided by the period. So we have learned that V equals lambda over the period. So I can rewrite this equation for P average to be 1 over mu omega squared a squared V. So this would be our average power. Or we can do a little bit of different forms of it when, let's say, we use our knowledge of V equals square root of F over mu, the force of tension over mu, and have the mu from here equals mu times V, which is in this expression, if I multiply this mu times V, that would be mu times square root of force over mu, which will give me square root of mu times F. So I can plug it in our expression of the power. So power average will be equal 1/2 square root of mu F omega squared a squared. So here's another expression for the average power. You want to take it into account. For three-dimensional waves traveling in an elastic medium, the mass m equals the density of the medium times the volume of that particular small slice of the medium. As this picture shows, this little rectangular slice of the medium has a surface area, let's call it S, and it has a length, which is this one, L in here. Let me just make a little bit more space for us. L, and this L is actually equals V times time. So this distance L is the distance that the wave travels in a time t. So L equals Vt, as I said already, and the volume of this element equals the surface area times the length. So then if I plug that into the expression for mass, that would be rho times V equals rho times S times L, and equals rho times S times Vt. Now, to find the average power by the three-dimensional wave, let's write the energy. So we know that the average power would equal energy per time. So, and let's see let's see if we can find the energy of a three-dimensional wave. So we know that energy equals 1/2 of a wave, mu omega squared a lambda. Now we can do a little manipulate this equation. So we know that the mu itself is m over L, and the lambda I can write as V times T. Now, and then if I plug in the RSVT into the equation of M, let's see what we'll get, okay? So here we have energy will equal 1/2. So what do we have? Instead of mass, I'm gonna write rho S. Actually, it would be easier if we put not SVT but rho SL. That would be much easier for us. So I'm gonna yes, so I'm going to substitute the M with the rho SL. So let's see, rho SL divided by L, because I want to cancel the L out. And then for the omega, oh, there is another thing that we need to remember. This omega itself, I can write 2 pi f. So you should remember that. Then I would have a 2 pi f squared a squared vt. Okay, seems like everything is correct. Oh, I forgot, there should be a square right here. Okay, so the else cancels out, and then for the energy, to beautify it a little bit, so 2 pi squared to 4 pi squared times 1/2, it's a 2 pi squared rho S rho S A squared F squared and VT. Now to write the average power, we say energy per time, and we plug this above expression into this power expression. We will get 2 pi squared rho S A squared F squared and V, because the T's will cancel out. In a different pencast, I will solve a problem. What is the average power that ocean wave hits a human chest, for example? Check my other videos, pencast videos for that solution. So now finally, let's talk about the intensity. How intense is this? So the intensity of a wave is defined as the average, it's denoted as a capital letter I, and it's defined as average power per surface across per unit surface area perpendicular to the direction of energy flow. So surface area perpendicular to the direction of the energy flow. So then if I plug that the expression for average power, then I would end up having 2 pi squared rho A squared F squared and V. So now if the medium is isotropic, which means same in all direction, That means the wave from a point source is a spherical wave. This picture represents a point source, and I took like a sound source right here. Let me use a different color. Sound source, something like a source that is sending a wave, a longitudinal wave. Later we will learn that the sound waves are longitudinal waves, and they are three-dimensional. So as the wave moves outwards, the energy it carries is spread over a large and a larger area, since the surface area of sphere is 4 pi r squared. Thus the intensity for that would be equal average power divided by 4 pi r squared. If the power output is constant, then intensity decreases by the r squared. So in other words, I can say intensity is inversely proportional to the 1 over r squared, which means the greater the radius of the sphere, the less is the intensity. So let's consider different radii. Like, for example, in this picture, here we have a distance from the point source with the radius r, and then you double the distance, which means the sphere is 2 times larger in radius. Then you will end up having the 2 times larger radius. Intensity is gonna decrease by 1 over 4, because if you put the 2 here, then intensity will decrease 4 times. If you triple the distance, the radius, then the intensity will decrease 9 times. So let's write this for the intensity 1, which is power average over 4 pi r1 squared, and then intensity 2 equals, for another sphere, power average divided by 4 pi r2 squared. So if we consider these 2 points, and then let's try to find the ratio. So I2 divided by I1 equals power average divided by 4 pi r2 squared divided by 4 pi r1 squared. I'm sorry, P average divided by 4 pi r1 squared. So this will lead us to have r1 squared divided by r2 squared. So thus, for example, when a distance doubles, r2 over, let's see, hence when distance doubles, which means we have r2 divided by r1 equals 2, then the intensity is reduced by 4 times. So then we will have I2 divided by I1 equals 1/2 squared, which is 1 over 4. So the amplitude of a wave also decreases with distance, since the intensity is proportional to the square of amplitude. Like if, where is our intensity? So you can see our intensity is proportional to the amplitude. So as the intensity decreases, amplitude also decreases. So let's just write in here, intensity is directly proportional to the a square. The amplitude since this is valid, then we can say amplitude also inversely proportional to the r. To see this directly, let's consider again two different distances from the source, and we call these distances r1 and r2. For constant power output, let's say power average will give us S1 A1 squared two pi rho and V and F squared. So I tried to I manipulated the expression a little bit so we can easily see what's going on. And then power average for the second one, I can write S2 A2 squared. The remaining is constant because we have the same material, the same wave with the same frequency. And then if we make these left parts equal to each other, then the right parts will lead us to have S1 A1 squared equals S2 A2 squared. So remember, A1 and A2 are the amplitudes, and S1 and S2 are the surface areas, and each of these equals 4 pi r1 squared. This one equals 4 pi r2 squared. Okay, so if we substitute that, we will end up having r1 squared a1 squared equals r2 squared a2 squared. So from here I could say a2 over a1 equals r1 over r2. So similar expression as we got for the intensity, which is somewhere here, like right here. So when the wave is twice as far from the source, the amplitude is half as large, and so on. If it's 3 times far away, then the amplitude is 3 times. So there is only one difference. The intensity decreases by the inverse square law. The amplitude decreases inversely, just simply inversely. Okay, so pretty much you wanna, what I just said is implied in this expression. A is related to the R with the inverse law, and then let me just write right here, intensity is inversely proportional to the square. So these two things.